Alright, today we're going to start the last section on limits and their infinite limits. So what I'm going to be talking about today is what happens when you don't get that definite answer of like 3, 5, 1/2, whatever the case might be, like we have been getting. So the first example I'd like to look at is in a chart form where basically I'm finding the limit as x approaches 3, and you can see that or negative 3, because this is approaching negative 3 from the left, and this would be approaching negative 3 from the right. And so what I'm going to do is look at this function and see what's happening at negative 3. So we're really looking at the limit as x approaches negative 3 of x over x squared minus 9. Now, one of the things that you may or may not recognize about this right now is if I was to look at this analytically, okay, I would be able to factor the bottom into x minus 3, x plus 3, but it wouldn't reduce anything on top. Therefore, I know that there's some asymptotes that are taking place here. So because nothing reduces, I've got to look at it numerically. This is called numerically when you're actually just sitting there and plugging in numbers as they get closer and closer. Now you'd use a calculator to do this. I've already used a calculator, so I'm going to just fill these in. So this first one, as I'm getting closer and closer to negative 3 from the left, I first start with negative 1.077. My next number is negative 5.082. The next one is negative 50.08. And the next one is negative 500.1. Then from the right, I have, starting with the furthest right, 0.9091. Then I have 4.915. Then I have 49.92. And then lastly, I have 49.9. Now I can show you guys how to use a chart method on your graphing calculator to get these answers much more quickly. Remind me to do that during class. You need to make notes of that off to the side in your notes and say you need to show us this. So really what I've determined here is that the limit as x approaches negative 3 from the left is equal to, this number just keeps getting bigger and bigger and bigger, more negative. So it would be negative infinity, while the limit as x approaches negative 3 from the right is infinity. Now because these are going to two different spots, this limit up here actually does not exist. So if you're talking about going from both directions, the limit does not exist. The next thing I want to look at is just finding some vertical asymptotes. Vertical asymptotes occur when the bottom does not cancel with the top, and you get a 0 on the bottom of the fraction. In this first problem, there is no number that when I plug in, I will get 0 on the bottom, because this number right here would have to be a negative 4 for me to get a 0 on the bottom, and x squared will never equal negative 4. So this one has no vertical asymptotes, and I'll just write that. Has no vertical asymptotes. My second problem here, I will look at the bottom because that's where I'm concerned at for vertical asymptotes, and this factors into s minus 5 and s plus 5. The top does not factor, nor does it reduce with the bottom. Therefore, there's vertical asymptotes at two spots. There's a vertical asymptotes at s equals 5, because I can get a 0 on the bottom with a 5, and s equals negative 5. So there's two vertical asymptotes on that particular problem. In my next example here, I have the top, which will factor into x minus 2, x plus 2, and the bottom looks like it may not be factorable, but since it has 4 terms, what I'm going to go ahead and try is grouping And so grouping method is when you take the first two and group them together and the last two and group them together. Well, I can take out an x squared and I'm left with x plus 2. I could take out a 1 here and I'd be left with x plus 2. So this does factor by grouping. And I get x squared plus 1 times x plus 2. Now these do cancel. And because they cancel, this actually creates a hole and not an asymptote. Therefore, there are no vertical asymptotes. No vertical asymptotes. I kind of jumped over the other part of the bottom, but I'll go back to that. There's nothing that will create negative 1 right here. Nothing squared will make a negative value. Alright, this is where I left off, and it was a good place to pause. What I wanted to do was take an opportunity to try to put this in the graphing calculator because it's much easier to look at on a graphing calculator. So what I've done is go ahead and graph this, and you can see up here that I've graphed the tangent of x over x. And what I want you guys to see is that it does have asymptotes. You may not be able to see exactly where they are at, but there's asymptotes and there's periodic asymptotes. So what we're going to do is use a trace to kind of figure out where those occur. So I will go ahead and trace this right here, and if you look, it's at 1.531 right there, and then if I jump down, it's at 1.6. So pi divided by 2 is 1.57. So I'm pretty safe in saying that this is going to be at pi over 2 that we have an asymptote. And then what I'm going to do is keep going down the way here and see what happens down here. So if I'm tracing this, it looks like I've added 3.14. So we know that trig functions are periodic and they're based upon pi and pi over 2. So the answer that I can write very quickly on this is that there are asymptotes, vertical asymptotes at pi over 2. And then plus, we can just go ahead and write it this way, n times pi. Okay, I could put n is any integer. That'll take me forward on the graph and backwards on the graph because not only is there asymptotes here at 3 pi over 2 and pi over 2, but there's some at negative pi over 2 and negative 3 pi over 2, and so that's taking care of all those cases. Okay, then looking at my last slide here, I've got two problems where it says figure out if the function has a vertical asymptote or a removable discontinuity. Removable discontinuity is a hole. So something that when you reduce, okay, so I'm going to go ahead and factor the top here. When I factor the top and I look at the bottom, if the bottom cancels with the top, this is considered a removable discontinuity. So at x equals 1, negative 1, it's a removable because it canceled with the top. Now you may not be able to tell as much on this one, so you may want to check it with the graphing calculator. At first glance, I would say it's removable, but we'll go ahead and check that for sure. So I know you can't see what I'm typing in, but I'm getting ready to type in sine x plus 1 over, so divided by x plus 1. And I'll enter that in, and I'll hit graph. And you can see this is what I'm graphing right here. The concern would be, remember I'm looking at x equals negative 1. And we're trying to see if it exists right here. It looks like it exists. And there might be a hole there. I'm pretty sure there is. But it'd be a removable because there's no asymptote there. And that's really all we're concerned with. So I'll go ahead and write that this is a removable discontinuity at x equals negative 1 based on the graph.